Hello, you guys back?
Yes.
Okay, good. Try to figure out how many people's in my class.
$43.
Okay, let's try to see how many people's actually here. So if you saw something pop up on your screen, no, I don't record the lecture. So that if you guys want, you can record them yourself. Anyone haven't answered my question yet? One, two, three. Okay, so I got a 47 student actually in here. Some of you probably log in, then go for a nap or something, right? Okay, doesn't matter. And you guys are all, yeah, as long as you pass, I really don't worry about. Just if you don't pass, and then you're gonna be in trouble. You cannot say, yeah, Jack, I need a 1 mark or 2 mark to pass. I will tell you, sorry, can't help you. Okay, we're gonna continue on. I think maybe I should answer someone's question first. Yeah, as long as I just try to say if you guys how many people actually here, but I don't really know who answered yes, who answered no. I didn't check. So the question someone asked in the morning that calculate the RTD resistance. Yeah, I can do that again. So someone asked me a question. I'm gonna be doing that. I think I did, but they said I use somehow different type of formula. So in the real this question, the real formula they or the book use this formula. Stop sharing. Is this one? Sometime I think people gonna stuck this. Oh, what's the input? What's the output? My thing is, you don't really need to worry about what's the input, what's the output, because for this question, they want you to find out the resistance, right? So resistance, you have a temperature, and you could thinking resistance is your output, and the temperature will be your input. So to use that formula, you could say, okay, resistance is your output span over your input span. Then here's your input value, subtract input 0, then plus the output zeros. So here I think might be causing little bit of thing is this formula giving us a different than I think I gave you a working sheet also. This morning I did is I used the resistance. I used the input, subtract the input 0, then over the input span. Then I move the output span actually to here. Then plus the output 0. These two formula is actually just switch between you have a something on here, something here. So it's just basically switching between these two parts. Yeah, and this is the formula they give you in the book, and also this is the formula on that PowerPoint. But this is a modified one. It's I personally I like this one a little bit better because you're using the same thing to compare down here. Then you try to calculate the thing is always outside there. And for this one, sometimes people will get confused. Okay, which one should I use for input and output? So if this one, you just compare your temperature because this is 11.4 degree for that one. The bottom gonna be 25 degrees subtract 0 degree. So it's all the degree on here. Then here, this is all your resistor. So it's somehow kind of like make more less chance you will make a mistake. I don't know if that helps. We good? Okay. Output gain? And no, we never talk about the gain in this one. Output span. Yeah. Okay. We come back to PowerPoint. So this is a Aurific flow meter. We just use to measure the two pressure. We have a Aurific plate in the center, and there is. I think I showed you that Aurific flow meter how it works. So we can move on. Here's how we're using that volumetric to measure the flow speed because we have two pressure sensor down here. Even this one, they are now using the Aurific. They use that vertical. What's the another fancy name? It's called. Sorry, my So one of the down there. Okay, it's called a Venturi tube. So this is a Venturi tube. In this picture, I like you guys to pay attention to a few things down here. Yeah, thanks, David. So first, we have a 2 bellow pressure sensor down here, and the center part is a linear variable differential transformer or linear voltage differential transformer. They try to measure the pressure difference on both sides, and this is try to converting that into electrical signal. The thing here is we know usually those LVDTs, they give out the AC waveform, but in here we put the 2 dials on here. So the dial is try to converting that AC signal into a DC signal. So pressure difference between this wider area and the smaller area, we cause the bellow to move the shaft. So because this area always have a high pressure, they will move this to push to that side. This side have the low pressure. And the core of LVDT, so change the DC voltage and the polarity. So because these have dials, so instead of AC output, now become DC voltage output to indicate the rate of the flow. Without those dials, you're going to output AC, but with the dial in there, they become the DC. Most important thing is down here, the signal output. If your flow is decreasing, the pressure will decreasing, so your output DC value output will decreasing. Make sense? So if you have a high flow rate, the pressure will be higher. This side, the pressure difference will be higher than this side. So you will have a output a higher DC value. But when the flow rate decrease, the pressure on both sides decrease. But it's a decrease more on this side. So you're gonna have a lower DC output voltage. Okay, so that's a very important thing to understand how this thing works. Do you guys get it?
Yes.
Okay, good. And if they ask you the output is DC or AC, you gotta pay attention to those 2 dials down there, right? Because the dial is gonna be output will be the DC value instead of AC value. Okay. So if you get this question wrong, someone gonna drive into your house with a ruler.
Hey, sorry, Jack, the signal output with the decreasing flow be DC value, decreasing amplitude. But what did you say for AC?
Because the dial down here, so you're not gonna output AC. It's gonna be output DC.
Okay.
Yeah.
Thank
because it's a kind of like a multiple choice question, right? So for multiple choice, they could give you the answer is a decreasing AC value or decreasing DC value. That's why I try to emphasize there's a dial in there, so it's a decreasing DC values.
Okay, gotcha.
Okay, another type of meter. They call the pitot-static tube. They have two measure the two pressure, the difference. One is where there's opening directly facing the direction of flow. So the liquid or gas we go into this center portion. That will be the high pressure tab for the measurement. And at the side here is not directly facing the direction of liquid flow or gas flow. And they have opening here. So when this liquid or gas goes through here, because there's opening here, they're also gonna go in there at the both sides, the top and the bottom. They're gonna have a pressure down there. But the difference between these two pressure, they can also using to calculate the flow rate. So this is a different type. They call the dynamic velocity impact pressure measurement. We have other type of the flow meter. This called a variable area flow meter. This flow meter is mainly used for indicating purpose only. It's not using them for like can be give out any anything like will be used for a transducer or something. It basically you just have to watching. They have a scale down there. You're watching this floater. When there's no flow, the floater gonna setting at the bottom. When the flow increase, this floater gonna try to rise until they have a stop on the top because you don't want that to go anywhere else. Oops. Okay, give me a second. I can show you a video talking about this type of flow meter.
Hey, Jack, can I ask you a quick question?
Variable area.
Yes.
It's kind of unrelated, but not really. I just noticed with the first test, there was lots of questions that would like it was a lot of the wording was kind of there's just a lot of it, I guess. And a lot of the things I was like, okay, I like for that all of the above you were saying, like some of them were so close and there was just one thing off that I couldn't find reference to. Like, so would you say that if it's got more parts than not, all of the above is probably the best answer to go with, right?
Because it's a different exam, right? I couldn't answer exactly what happened on the. You guys did the high voltage exam, right?
Yeah.
I couldn't answer what's really happened on the high voltage exam. I never taught that topic, and the high voltage is being taught by lots of instructor, lots of people putting the question in there. So you might have an instructor is really picky. He will put some kind of tricks in there just to separate that one. But I can tell you is this automatic control is made by Alan. Alan is also he's kind of we are more alike. We think the student only need to know the basic. Okay. We are now trying to trick you guys.
Okay. Yeah, that's basically answers what that's perfect. Thank you.
Yeah.
Flow meters are used to measure the volume flows of liquids and gases. They consist of a vertical conical measuring tube which widens upwards and a specially formed float which can move up and down freely in the measuring tube. Together, the reference position of the float and the measuring tube create a variable ring orifice. The higher the position of the float, the larger the ring orifice, and therefore the cross-sectional area through which the medium can flow past the float. This is the origin of the English designation of the device. When there is no flow, gravity keeps the float at the bottom end of the measuring tube. As soon as the medium flows through the tube from bottom to top, the float rises again, until the acting forces are in balance. I'd like to explain this in more detail. Three main forces act on the movable float. The gravitational force W, weight, operates downwards as the reset force, whereas the buoyancy force B and the flow force D, drag, work in an upward direction. The position of the float is a flow indicator. The gravitational force and the buoyancy force are constant for a specified application.
Oh, okay. Oh, okay. Just give me a second. You guys can hear the sound, right? But just cannot see the move on there.
Yeah, that sounds good.
Okay. Let's. Oh. Just try to start again. Yeah, that's why I like to open the chat so I can see.
Variable area flow meters are used to measure the volume flows of liquids and gases. They consist of a vertical conical measuring tube which widens upwards and a specially formed float which can move up and down freely in the measuring tube.
Is the video
Together,
still not moving?
the reference position of the float and the measuring tube create a
Same thing?
Yeah, same thing.
Okay, let me see. Might have to refresh the page. Give me a second. Let's try.
Variable area flow meters are used to measure the volume flows of liquids and gases. They consist of a vertical conical measuring tube which widens upwards and a specially formed float which can move up and down freely in the measuring tube. Together, the reference position of the float and the measuring tube create a variable ring orifice.
Okay.
The higher the position of the float, the larger the ring orifice, and therefore the cross-sectional area through which the medium can flow past the float. This is the origin of the English designation of the device. When there is no flow, gravity keeps the float at the bottom end of the measuring tube. As soon as the medium flows through the tube from bottom to top, the float rises again, until the acting forces are in balance. I'd like to explain this in more detail. Three main forces act on the movable float. The gravitational force W, weight, operates downwards as the reset force, whereas the buoyancy force B and the flow force D, drag, work in an upward direction. The position of the float is a flow indicator. The gravitational force and the buoyancy force are constant for a specified application. Only the flow force can vary temporarily, as a result of a change in flow which moves the float into a different position.
Hold on a second. I think something's wrong with this one. Okay. My computer was
I would like to illustrate this with an example. Let's take as our starting point a state of equilibrium of the forces. That is, the float remains immobile in a certain position with constant flow. If the flow increases, the flow velocity in the ring orifice also increases, and correspondingly the flow force as well. The float rises. With the higher position of the float, the ring orifice, however, also becomes wider. So the flow velocity in the orifice sinks again, and the flow force returns to a state of equilibrium. The physical operating mode shows that the position of the float is a flow indicator. With glass cones, the flow rate can be read on a scale on the measuring tube itself. With metal cones, the float is not visible, so they have a magnetic transfer onto the pointer. For this purpose, a magnet is built into the float. Through a magnetic coupling installed on the pointer axis, the linear movement of the float is converted into the rotary movement of the pointer, which displays the flow on a scale. Once again, no auxiliary power supply is required. Let's sum up again. The example illustrates that the operating mode of a variable area flow meter to measure and display flow is purely mechanical and without auxiliary electrical power. This is an important unique selling point for variable area flow meters.
Yeah, so this just a explanation of that. I don't know why they kind of got stuck down there. Okay, next one. We go back to our PowerPoint. So another one is called a turbine flow meter. This turbine flow meter is also an important thing to know. Here the picture. They have a magnetic pickup and they have a turbine inside. When the liquid goes through here, turning the turbine, and the magnetic pickup can pick up the pulse with the turbine turning speed. So whenever turbine pass through there, they're gonna pick up a signal, and you basically based on how many pulse you pick up down there, you're gonna be censoring the flow rate. But the detail I can show you in a video. So here's a few things is the output is a digital pulsed output signal. So they give you like maybe a square wave or maybe some kind of waveform digital pulse. Very accurately, good that expensive. They have to operate with a clean flow, but you have to understand the basic is how they thing going to sending out a digital pulsed output signal. So we can watch the video. I hope the video can explain better than me. That's always the case.
Series meter housing is cut away in this animation. We see a cantilever type design where the multi-bladed rotor is supported by an upstream stator. The stator also channels the flow stream, depicted by the flowing blue arrows, through the rotor. The rotor is hydraulically balanced and floats on a virtually frictionless, highly polished tungsten carbide bearing. The rotational speed of the rotor is directly proportional to the axial flow velocity of the fluid. The rotor has a number of equally spaced blades that are made up of a paramagnetic material. A pickup coil is located directly above the rotor and is completely isolated from the fluid. It is constructed of many coils of fine wire that are wound around a permanent magnet. As each blade passes underneath the pickup coil, it passes through the magnetic field. The continual passing of the paramagnetic blades under the coil induces an AC voltage in the coil, which is seen as a sinusoidal wave. The sinusoidal wave is then converted by the preamplifier into a square wave pulse stream, as shown. Since the flow area is constant and the rotor velocity is directly proportional to the flow velocity, each output pulse represents a precise amount of fluid that has passed through the meter. The continuous pulse stream is then transmitted to an electronic counter or flow computer to indicate both instantaneous flow rate and total metered volume.
Okay, so I think Zah explained better than me, right? Yes. So they use the metal blade down here. So each blade is they call the paramagnetic blade. So these have a magnetic pickup. Those one have the each time when the blade passing through that magnetic pickup, it will induce a voltage in the sensor, and that sensor gonna be receive a signal just like a generator. You can generate a voltage waveform, but for that voltage waveform, they through the signal condition to change it to a square wave for better processing and calculation. Converting into this, the whole thing is the flow, because the flow gonna push the turbine to turn. The turbine turns, each turbine have a lot of blade on there. Each blade goes through that sensor, going to induce a voltage in there. And the induced voltage in there is a digital pulse signal, and they will condition the sine wave. I think the radio said it's a kind of like a sine wave signal, but they will change it into a square wave signal. That answer your question? Yeah. The output is a square wave. Yeah, in here, the output will be square wave. The magnetic pickup here, it pick up the sine wave. The pulse stream, it depends on where you look at it. If on here, it's a sine wave, but they convert it into a square wave, go to the output. And actually for you don't need to worry about it's a square wave or sine wave, because generator always a sine wave. And to make those waveform useful, easy to count, because you have to count how many waveform is there. That's why we try to, it's easy to count the square wave. That's why this transducer, this flow meter, the output will be the square wave. Square wave you can think is AC, doesn't matter. The square wave is really hard to see, because if all above zero, you can call it a DC. It's a half above zero, half below zero, you can consider it's AC. But the main thing for this turbine flow meter is, if you look at this picture, you have to be able to identify this is because for sure I'm not going to give you this turbine writing down here. So you have to understand it's a turbine flow meter, and you have to understand it's the output is a digital pulse. And you'll have to be able to answer if the flow rate is low, the pulse will be low, and if the flow rate is high, the pulse will be high, as counting by the numbers. Yes, if not important, why I spend so many time try to make sure you understand this? Another one is called a magnetic flow meter. And we also have a video for the magnetic flow meter. The magnetic flow meter is they usually when the liquid in there is somehow is conductive fluid. So because you have some kind of I think they call it what's it called, the electrode mount on there. So you will causing the conductive liquid to go through the magnetic field because these electrodes will causing current to go through the conductive fluid, and when the current goes through the magnetic field, they will causing the distortion to the original magnetic field because the current have a field, the original electromagnet will have another field. The distortion of the field can be used to calculate the flow rate. I think I have a video down here. Oops. Oh shit. Can you guys still hear me?
Yep.
Okay, I think something happened on my Zoom meeting here. It said stop walking. Okay, let me see if I can play this video or not. Zoom does not like I play the video down here. Can you guys hear me?
Well,
Yep.
we can only hear you when you ask if we can hear you.
Oh, okay.
Are you saying things in between that?
No, I think when I try to play the video, it kind of stopped me.
No, we can hear you, Jack. It's coming in perfect. Just nothing's happening on your screen or anything.
Okay. Try one more time. Doesn't work. I will stop play this. Maybe I will find on the YouTube to show you guys. Yeah, I don't think it works.
We can see the video if you just try pressing the play.
Yeah, I was just gonna say that. Oh, there you go. Yeah, that's all it needed.
Can you guys hear?
No, no audio.
Nothing?
No.
Check the volume. Oh, okay.
Try one more time. Yeah, just let me know if you can hear any sound or anything.
Of this principle can be traced back to the English physicist Michael Faraday, who in 1831 discovered that electrical current can be generated with a magnetic field. Roughly 100 years later, the Swiss inventor and priest Father Bonaventura Turliman applied this knowledge to electrically conductive liquids flowing in pipes and built the world's first electromagnetic flow meter. Let's take a closer look at how this measurement method works. Two field coils are located inside each electromagnetic flow meter. With the help of what are termed pole shoes, these coils generate a constant magnetic field over the entire cross-section of the measuring tube. Two electrodes which can pick up electrical voltages are installed at a right angle in the wall of the tube. The lining fitted on the inside wall prevents electrical short circuits between the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water with red and blue particles. However, as soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline. Together with the known tube cross-section, the flow volume can then be calculated. greater the flow velocity, and thus the separation of the charged particles, the greater the electrical voltage between the electrodes. The electrodes also detect what is called interference voltage, which has to be separated from the actual measuring signal. One method that has been successfully used for this purpose is to create the magnetic field with a pulsed direct current. To do so, the polarity of the magnetic field is alternately reversed, illustrated here in slow motion. The voltage picked up on the measuring electrodes now constantly changes in polarity. As a result, all constant interference voltages can be eliminated. For example, electrochemical effects in the liquid, or external electromagnetic fields. Thus, the size of such interference voltages has no impact whatsoever on the actual measuring signal. The advantages of this are a stable measurement and a stable system zero point. With an installed base of over 1 million electromagnetic flow meters, Endress and Hauser has stood for flow expertise and superb product quality for over 30 years. In other words, high accuracy.
So that oops. That's the magnetic flow meter, and I think I might made a mistake when I explained to you, so I will be sure make sure I don't say something before watching that video. But the video pretty much explained to you how that used to measure the flow meter by using the magnetic field and induce the voltage across the two leads down here. And if you have a fast flow rate, the voltage induced is going to be higher. If you have a small flow rate, the voltage induced is going to be lower. And they can use alternating magnetic field, try to eliminating any other noise or interference. Another one is called a Vortex shading flow meter. It's also using a different kind of technology. They put some kind of obstruction in the center when there's they're causing some kind of obstruction for the flow, and they were creating those vortex, and the frequency of the vortex generated down there can be used to measure the flow rate. And I think I have another one to show you down here. Is maybe I opened too much things, so that's why it doesn't work for me anymore. Vortex flow meter. Okay, the electronic circuit convert the Vortex sensor converts. Which one? Oops, I didn't see you guys chat. A. Oh, sorry. A should be. It's a velocity into volumetric flow rate. And the volumetric flow rate determined by the frequency. So this is a small explanation down there. So that's how they use this Vortex shading Flowmeter to measure the flow rate. And advantages, disadvantages, it's on your textbook. Then we have an ultrasonic Flowmeter. Ultrasonic Flowmeter have two types. One is called a Doppler type. Doppler Flowmeter is they sending a signal and calculate the Doppler frequency shift. So they send the signal here because the liquid flow here. We move the signal, the receiver is here sending, bounce back, and a different one, transist time Flowmeter is they try to use this one, send here, receive here, this one, send here, receive here. They have their own usage. This one cannot use on the clear fluid. They have to contain some kind of particles. This one must be using on the clear fluid. If they contain particles, this one is not going to be working too good. I think I have a ultrasonic Flowmeter. Let me see if I can find that.
Sound, published in 1877, describes
Can you guys see?
Yep.
Yeah, that's good.
Okay.
the propagation of sound waves in solids and gases. Here is how this measurement method works. Inside the ultrasonic Flowmeter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternately transmit and receive an ultrasonic signal. Simultaneously, the transit times of these signals are measured. The ultrasonic signals are generated with piezoelectric crystals applying a voltage. Conversely, a piezoelectric crystal creates a voltage when an ultrasonic signal impacts the sensor. By increasing the number of sensor pairs, it's possible to accurately detect and mathematically compensate for flow profile distortions over the entire pipe cross-section. When there is no flow, the signal transit times are the same, upstream and downstream. Once the fluid starts to flow in the measuring tube, The ultrasonic signals are accelerated in the direction of the flow and decelerated against the flow. As a result, the ultrasonic signals now have different transit times, less time in the direction of flow and more time against the flow. Therefore, the differential transit time measured by the sensors is directly proportional to the flow velocity in the pipe. Together with the known tube cross-section, the actual flow volume can then be calculated. The greater the flow velocity, the greater the measured time difference between the two ultrasonic signals. For ultrasonic flow measurement, the sensors do not necessarily have to be fitted into the pipe wall. With a clamp-on system, for example, the sensors are fastened directly onto the outside of the pipe. They can be retrofitted at any time without interrupting the process. With clamp-on sensors, the ultrasonic signal is passed directly through the pipe wall and into the fluid. The signal continues through the fluid, is reflected on the opposite pipe wall, and then measured by the second sensor, in this example, with a two-traverse installation. The clamp-on design is unique because flow rates can be measured in very large pipes, up to 4 meters in diameter. This possibility increases the areas of application, for example in the water and hydroelectric industries. Flexible mounting, process safety, and cost effectiveness are the distinctive advantages of ultrasonic flow measurement.
Okay, so the video kind of explain how it works, and those are video is much better, can explain those things than a book or than I can do it. Then you have those they call the total flow measurement. It's a different type of device used to measure the total accumulated flow. They call the positive displacement meters. So basically, they separate that kind of like a pump. They have each chamber. The volume of the chamber is null. And when the liquid or gas into each chamber, they just push that thing to turning. And this side will fill the chamber. This one side will empty the chamber. And by counting how much times per minute the chamber is rotating, so you know how much volume or how much total material is goes through this one. That's how they calculate them. Don't have too much things on there, guess. Then the mass flow. Mass flow is they use a different type of mass flow meter. They based on the relation mass flow times mass density. They just calculate what's the mass flow down there. I think that's it for that's everything for module 4. Module 4, so it's a smaller section. It's a pretty complicated, but we only want you to know some basic, like the picture I showed you before. That's important to know, and the turbine, flow meter, how they work, and magnetic may not be so important, and the formula showed you how you're gonna be identify each component in there. And I think is a lot of Vortex Flowmeter. For the Vortex Flowmeter, how they calculate, how they figure out the flow rate is by measuring what? Anyone? Yes? Yeah, the frequency, right? The frequency of those voltical generator produced by the can look that again. Yeah, the frequency of those volticals, how much they produce down there, because if you have a higher flow rate, they can produce more of those. So the sensors down here is try to detecting the frequency of them. So here is frequency of the volticals detected by the sensor. So this is important to know. I guess that's about it. And let's take a coffee. Can you go back again? Okay. Maybe let's take a coffee first. Then we come back. Come back at 12:49. Yeah, then if you want, I can show you that one again. Then after that, we're gonna go to module 5.
Yeah, quick question, Jack, before you go
Yeah.
here.
Yeah.
All the questions actually that are in our book, are those good to do? You think those will help us a little bit, or?
It's the book sometime, because you can see module 1 and 2 we go lots of detail, but later those modules we not go so detailed into them. So some of the question is good, but not all of them. The best way is you can try to do those online quizzes. Those are much more, because this book, if you look at the title, it's also for electrical computer engineer technology. So we use the same book. It's for the instrumentation guys, and it's for we using as automated controls.
All right.
Okay. Also, I think 351549, he raised a hand. You have a question? Or you want to ask me after the coffee? 351549. Who is that? Yeah, we'll talk about after coffee. Hey, so sorry, I missed a little bit. And so, Sean, you want to say that thing again? So that's where it says convert the frequency from the pressure. Good. You're welcome. 351549, you have a question? Hello? Is he here or no? You raise a hand. I think the name was 351549. I don't know who that is. Should I kick him out of the class? Yes? Y'all agree? Could do that. Remove. He probably not here. Felicia. Who's Felicia? Okay. I also put the waiting room on, so he cannot come back. So for module 3, module 4 is the smaller section, and they have a lot of detail, but for us as electricians, especially we are in the construction program, we don't need to know all those detail. All we need is have some basic knowledge in there. And as I think Hayden asked me, that we give you lots of trick questions? No, we're not gonna give you lots of trick questions. We just want you to know or understand the basic. So, like I mentioned to you, I think you will have about 5 questions from module 3 and just 3 questions from module 4. Now, if you guys are good, we're gonna go to module 5. So module 5 is about the temperature sensor and the transmitters. Temperature is something you cannot measure directly. We always say, oh, we try to measure the temperature, but it's not actually you are measuring the temperature. It's the measuring of temperature is by observing the effect of different material and some of radiation of the energy, some of the conducting of the energy, some. So you actually is try to measuring the heat energy given out by a body. There's a non-electrical measurement and the electrical measurement. Non-electrical measurement is like you have a glass stern thermometer. When the temperature changes, those liquid. Is this the PowerPoint from module 5? Yes. Did you find out on the D2L? No. You don't have this page? Okay, give me a second. D2L. Module 5. Okay, now you find it. That's fine. So because the temperature increase, we causing those liquid inside the glass stream to expand. So they can use to indicating the changing of the temperature, used to measure them. Also the pressure, sometimes you will have those liquid gas inside, and they will, when the increase of temperature is actually means they have more heat energy in there. So they will expand, they will causing some filling the bulbs or capillaries. And this one we all know, changing the shape, because you guys go through motor control in the last 3 years. You learn the bimetallic strip for overload of the motor, right? Electrical one, that's the one we're gonna focus mainly on here, is thermocouple is changing of the voltage. And some of them we're changing the resistance. That's resistance, temperature detector, and the other are few of them. We're gonna talk in detail. Changing radiations. So this is it's a new one in the last 20 years. It's called an optical pyrometer. That's the fancy book name. And the regular use is you guys probably on some of the job you saw those thermal imaging finder or like a gun or something. It can be using, because usually people will use to check the connection inside the panel or inside the big junction box to make sure you don't have an overheat in those places. For that, it's also they will use the thermal imaging camera to show in different color. They can use the color to identify which point is hot, which point is cool. Selecting of temperature sensors, that's a pretty big thing because I think I showed you guys some of them that book down there for the thermocouple. You have a wide range of applications, so range of temperature depends on what's the measurement range there. You're gonna choose in different type of temperature sensor, and the speed of response is another consideration because temperature is not like we're talking about. It's not something you can measure directly. You have to wait for the heat energy to transfer from Bruce. Do you guys know Bruce? Okay. And okay, yeah, now I let him come in. Okay, Bruce, now you are in here, right? Did he get in here? Oh, sorry. Yeah, you're welcome. Yeah, if you get disconnected, you just can come back here. So we still haven't seen that guy with the number come back yet. So he probably not gonna show up here. We only have 47 people here, so there is people drop out. I don't think you're missing too much things. So the heat transfer, it's actually taking three different type of the heat transfer generally. One is conduction. If usually a solid piece material, you heat on one end, the heat going to be slowly move from one end to another end. This is considered as a conduction. Another one is called a convection. Convection usually happens in liquid. So either is water or gas. So you're heating something from the bottom. When the gas or liquid getting heat up, they will be they will become less dense. They will rise to the top, and at the top, the cooler one, we go to the bottom. So they have a circulation motion down there. That's the convection of fluid, either liquid or gas. The third one is the radiation. The radiation mainly depends on the color of the body. So if it's a black body, they will receive all type of radiation is an electromagnetic waveform. So the sun emit those electromagnetic waveform, it will reach the Earth's surface or Earth's air. Between the sun and the Earth, there's a vacuum space in there. So radiation can travel through vacuum or travel through anything, any object. If it's above the absolutely 0 degree, it will radiate heat energy out. At the same time, it will receive the heat energy. So the speed of response of those temperature sensor is you have to wait for the heat energy transfer from whatever the subject you try to measure to your sensors. So some of the energy will be transferred much quicker. Some of the energy will be transferred much slower, and it depends on what type of sensor you're using. Also, the condition of that, it all going to causing the speed of response in your application. Accuracy is another one, depends on if you just want to know something is warmed up or like a burner is on or off, you can use a very rough accuracy, because the burner goes on, it will be have a high temperature, the burner off, we have a low temperature. But if you want to know exactly what's the temperature in there, then you need a very accurate one. Mounting the sensor is also another thing. You have to be careful. But the majority of those things is gonna be focused on the people in that industry. They develop the sensor, they installing, using the sensor to control the process. For us, yeah, we only need to know some basic things. Mechanical expansion, temperature transducer. This is a bimetallic strip. So 2 different type of metal welded together. When you heat it up, one will expand more than another one, so it will deform, make a movement. It can cause an indication, or it can use to, mainly we saw them in the overload of the motor, right? This is you have a liquid and you have a gas inside this tube, and it's a closed tube, so they also call this the Borden tube. When the temperature increase, so the more energy we cause either this into vaporize to increase the pressure, or they will increase the volume to causing increase the pressure. And this Borden tube, when the pressure increase, it will try to expand or try to make a movement. You can use that one to indicate the temperature changes. So they can use the vapor pressure, because when violate the liquid, when the temperature increase, they will become the vapor. It's at the point when vaporization is so low, so they can change it to increase the pressure to causing that movement. Here is a mechanical expansion temperature transducer, or they use in here as a temperature regulator. So you have a cold air supply. This is like used in a heating system. You use the steam or steam supply to heat the coil, to heat in the air. So this is a valve down here. You have a sensing bulb down here. When the air got heated to a certain temperature, it will transfer the heat energy to the sensoring bulb. The sensoring bulb gonna be, when the temperature increase, it will creating higher pressure, go through this tubing. Inside the tubing here, you have a diaphragm on top. The bottom part is fixed. And when this increased pressure causes the diaphragm bend upward, because at the bottom you cannot move, so you only can go up. You will pressure the spring, and this diaphragm also is mechanically connect to those regulator valves. So if it pulls up, it will close the valve to close the steam, because your steam have to go through this opening valve to go to this coil. If the valve is closed and there's no more steam can go in there, and so you're not heating the air anymore. So this is they call the self-regulated. If the temperature is low, the pressure drop, the spring gonna push the diaphragm down, gonna open the valves, and your steam can go through the coil to heat the air. But if the temperature reaching your setting or whatever too high, you're gonna close the valve to stop the heating process. Mechanical one is a simple design, low cost. They usually use for local indication and control only, and the response speed is pretty low, slow, because you have to wait the whole thing, the energy transfer to the mechanical linkage, then they will expand or contrast, then it takes time to do that. Electrical temperature transducer, the most common selection of temperature transducers. We're talking about thermocouple, we have a resistance temperature detector, and we have a thermistor. All those three is very common, and for them, another one is called the IC temperature transducer. I don't know why it's not here. They have a wide measurement range, and the accuracy depends on which one you're using. Some are more accurate, some are more sensitive. Some can have a long-term stability. If you, I think on your module 5, at the almost end of your module 5, you have appendix tables. So appendix A. Appendix A is showing you the thermocouple table. You can see the temperature down there and whatever the voltage is going to be millivolts they're going to generate. So you can use that to calibrate or try to use them to measure the temperature. And the temperature is pretty wide. It's called a type K. There's other type of them. The lowest temperature on this table is negative 260 degree. The highest temperature on here is 790 degree. So it goes through a pretty wide range. And table appendix B is the RTD, the resistance temperature detector. And they also start from negative 200 degree. It all the way goes to, I think, 119 degrees. The third table, appendix C, is your thermistor resistance and temperature. And they starting at negative 80 degree all the way to positive 39 degree. So that way, this is just one type of those temperature sensors. IC temperature transducer. Yes, IC is the one they didn't. It wasn't. It's later on. It's on here, but in here, it's in your book they have that. So on the 5-12, you're talking about IC temperature transducer. It's called the integrated circuit temperature transducer. So to choose whichever the one you want to use down there, you gotta go to look in the detail, which one is have the measurement range matching your requirement, the accuracy, the sensitivities. Those are all important things. First thing we're gonna talking about is thermocouple. And I think I showed you a thermocouple before. That's in module 2. We're talking about transducers. So the thermocouple, you consider thermoelectrical temperature transducer. Okay. He should be come back. I think he's back here. So thermocouple, they use 2 different type of metal. And I think in chapter 5, also they have module 5, they have table 5-1. They showed you a different type of metal together. What's the measurement range down there? One junction is considered the hot junction, the measurement junction. That's where you're going to use that junction to make the measurement. And another junction is called the reference junction. The reference junction is for because you want to take out the ambient temperature effect in there. The important thing for thermocouple is we know you're going to generate a voltage or have a EMF. So the thermocouple is an active transducer. It will generate a voltage by itself. The generated voltage is proportional to the difference between the temperature of the 2 junctions. So you have a measurement junction, reference junction. The voltage depends on the temperature difference between these 2. If you know the junction, one junction, the temperature is known, the temperature of other junction, you can either from the table or from the calculation, you can get that. And the thermal pile is when you put several thermocouple together, they become a thermal pile. So it's good idea to know this. And I think I already showed you that day when I do the demonstration.
Hey, Jack.
Yeah.
I don't know if you can see that, but I think a couple of people got disconnected from the chat. Apparently.
I think I let them in already. I disabled the waiting room, so anyone want to come back, they can come back.
Oh, okay.
Yeah. Just when I kick that number guy, I don't know who it is. I enabled the waiting room, but after a while, because I know sometimes your internet connection is not stable or something, and I heard some people were driving out to order some takeout food from a restaurant. Probably not in my class.
No.
Yeah. So and also thermal pile is not on the PDF. So maybe purposely we didn't put that thermal pile on the PDF. So if you are in my class, I told you it's important to know that. And you come to my class, you know it. You can answer that question right. If you're not, sorry for that. And that's also another thing. Like sometimes people ask me, they say, "Hey, why can't you record the video and I can watch them later on?" I was thinking, if you don't have the time in the daytime, come to my class to listen to me, how you gonna find the time to watch recorded video yourself? Yes. So Jose, they all answer your question. So those are the active guy in my class. They all know that. You okay with that? Yeah. So maybe I purposely don't want to put that one on the PowerPoint you guys got. So you can looking through everywhere, you can find the right answer for the question. For the people come to my class, I have to give them like a benefit or bonus mark, right? Here is a displacement of you have a thermocouple circuit. So you have two different type of material, and this is where you're gonna make the measurement. Because you need to bring out to wherever the measurement point is, you use the copper wire. The copper is a good conductor. You don't want to creating too much because iron constant, those have too high resistance. So that's why later on you just use the copper as the conductor to bring the voltage out to your measurement. They talking about is because there's a cold junction down here, or there's a reference junction. They talking about this is put into the, if you want to measure accurately or at we call it absolutely or something, the temperature, you want to put this into a ice bath. The ice bath is a combine of water and ice together. In the renewable energy, we're gonna talk about that thing a little bit more. It's because if you have a pure ice, the temperature could be below 0 degree. Here is give you a 32 degree Fahrenheit. It's actually 0 degree Celsius. So if you only have water, the temperature could be above the 0 degree. Only when there's a mixing of ice and water together, the temperature is at absolutely, not absolutely, is at 0 degree. So that's where this measurement will be more accurately if you put the reference junction or another junction into this ice and water combination. Here's showing you electrical transducer. The same thing. This is a thermocouple. This is the junction you try to heat. And this is a cold junction you put into the ice and the water mixture. And the induced voltage down here, we show you what's the difference between these two temperatures. For the junction of those hot junction, you can just twist in the wire, or you can weld the wire, you can solder the wire together. For the actually application, you probably want to weld them together or solder them together. It will make them more stable and connected.
Hey, Jack.
Yes.
I I'm sorry to interrupt you, but I just was thinking about it. I have a friend in this class that had a power outage. She was
Yeah.
texting.
Yeah.
I'm just thinking if I should write down that last note for her.
Sure. So if he have a power outage, no problem. You like I don't mind if you guys share information together. And the only thing is sometime I know especially those online classes, you log in here, then you just leave your computer on, you go somewhere, right? So if you want to help your friend, I don't mind at all. Or if you want to help classmates in the class, it's totally fine with me.
Yeah, sorry, I just was wondering if you could just repeat. I know there's that one thing you were saying that for the people that are here. I was just wondering if you could say it again. I was going to write it down and just send it.
Who's your friend's name? You want to tell me? Who?
Paige.
K.
Paige. I'll type it in the chat.
Paige. Okay. Page. Okay. Yeah, so that's on this page.
Yeah, okay. If you just give me 1 sec.
Good. I
Yeah.
heard the camera.
Thank you.
No problem. We are here, right? Another thing is also this gonna be affect the response time, but lots of industrial installation is if you have a process, either a tank, a pipe, and you try to measure the temperature in there, you're not gonna just stick a thermocouple directly in there. Usually they will build a thermal well down there. The thermal well is they build into the tank or into the pipe, and your thermocouple is stick inside into the thermal well. They said make sure the front of the thermocouple is touching the thermal well. These have a multiple purpose. One thing is if you ever need to replace that or you need to change something, you can easily install and remove the thermocouple. And second thing is depends on what's in the process there. Like Alan, before he working in the beer brewer. So do you really want to stick a thermocouple into the beer someone gonna drinking later on? You can't do that, right? Because it's not meet the requirement for food processing. So they will use stainless steel to build that thermal well inside there. So you stick your thermocouple in there, you just try to measure the temperature, but you're not gonna contaminate wherever the food or the material inside the pipe or tank. But the thermal well also will affect how fast you can measure the temperature. If the temperature keep constant, it's no problem. But what if the temperature increase or decreased, and it take more time to go through the thermal well to conduct the heat energy through the thermal well into your thermocouples. Different type of thermocouple. Here is when you have the table on there, and when you're replacing existing thermocouple temperature sensor, if you use a different brand or different type, you need to recalibrate its reading, because every piece of equipment in that, especially if you want to get a precise temperature reading, you always have to make sure they are calibrate according to whatever you had previously, because you can see the different material, they will have different ranges. So when you're heating them up, they might generate different voltage down there. So that's the purpose for calibration. And for your question is, if I try to measure the temperature for the liquid in this pipe, this is the well. You can see this piece is the well. So the temperature have to, from this pipe, the liquid have to transfer to the well first, because this is the well, and then go through the well, go to the hot junction of your thermocouple. Okay. Yes, well is a tube. This well is a pre-made, because you want to measure the temperature. They will pre-made a well into this pipe. So later on, you can stick a thermocouple in there to measure the temperature. Good job, Lucky. Shin, you good? Yes, no, okay, yeah. Because you try to measure the temperature here. Let's say if here is a milk or is a beer, your thermocouple is industrial equipment. Do you really want to put that industrial equipment into your drinking water or drinking beer? No, right? You want to have some kind of food grade thermal well build up in there, so you're not touching the beer or milk down there. I don't know if you want to use that to add the flavor. You insert in there, you mount in there. If you want to replace them, you can just take it out. It's the way how the heat energy, because you measure the temperature, is not really measure the temperature, is measuring the heat energy. Yeah, the well is stuck into the pipe. They pre-made, they installed in there. So if you want to measure the temperature, you can just stick a thermocouple inside there. You have to make sure the end touching that wall there. So they can conduct the heat energy through there to there, so you can do the measurement. Yeah, David, that's a good idea, right? Otherwise, if you really have a good one stuck in there, what if you want to replace it? You have to stop the flow, you have to empty everything. Otherwise, when you open, all those liquid gonna come out. Here is the calibration is for, because you different type, they might give you different output voltage, even at the same temperature. So you have to calibrate to make sure the millivolts you're reading down there is meeting. Yeah, you can see here the K type the 500 degree here. Let's say we just draw a line down here, 500 degree. For S, gonna output this voltage. For R, gonna output this voltage. For K, gonna output this voltage. For J, gonna output this voltage. For E, they're gonna output this voltage. So you cannot just get a new one put in there. You have to make sure it's calibrate the millivolts to the temperature measurement. Electrical thermal temperature transducer advantages. Thermocouple, you don't need the power because it's self-powered, output voltage. Big temperature range, you can see from the appendix A, smaller size and fast response, kind of linear temperature down there. It's you can see here, they always have a certain range there. The temperature is very linear, but also you can see this J, for the smaller area, they are pretty linear, but for the big area, the whole temperature range, it's kind of curved, same as this E also. So that's why they said relatively linear. Low cost, long term, and if you put in some transmitter down there, or you have some kind of amplifier down there, you can use that for pretty long distance. There's the disadvantages. You need a compensation for the cold junction, low output voltage millivolts, and so it's really susceptible to any interference. It's a per every degree temperature changes, the change of the voltage is really low. So it's very hard to measure unless you have a really good transducer down there. It's really hard to measure smaller temperature changes. That's where they call the pool resolution. So if your temperature only increase 1 or 2 degrees, and now gonna give you, it's very hard to actually know in that smaller temperature changes, and the other more like the semester or semester usually it's pretty good. And then the new one, the IC one, they can tell you the temperature change in 0.1 degree, or even some industrial high accuracy one, they can even tell you in 0.01 degree temperature changes. Usually need a protective thermal well, special wire. Those things is but not too important to you. Next one, resistant temperature detector. The resistant temperature detector is because when they usually, it's a common type of metal wire type of material. It's because we know, and that's where we learned in year 1, right? Most of the metal have a positive temperature coefficient. So when the temperature increase, the resistance of the wire gonna increase. So they kind of use that ability to use it for measuring the temperature. Temperature induced change in resistance. So they said most metal increase, temperature increase. That's most metal have positive temperature coefficient. And the RTDs is using this property to measure the temperature. Because for the RTD, we want to accurately measure the temperature, we using this one we're talking about, Wheatstone bridge. So we have this is the resistance temperature sensor. We have another fixed or changeable resistance value to build a bridge down there. Then by measuring this voltage down here, we give a power supply. We can, based on this voltage, to convert into the temperature measuring down here. Semester. Semester is actually semiconductor material. The semiconductor material, this is a very sensible semiconductor material. When the temperature changes, the resistance of this semiconductor material will vary noticeably. So that's why it's very accuracy, it's very sensitive. And we all know the semiconductor material, if you come to year 4, you know they have a negative temperature coefficient. Is this very important thing? Yes, it is, right? So you can see when the temperature increases, the resistance of this semester actually decreases. For other two, when the temperature increases, the resistance or thermocouple is output is the voltage will increase. The RTD, the resistance will increase. For the semester, the resistance actually decreases. So this is a very important thing to know. You're probably going to get a test on, so be careful. Semester also it's extremely non-linear device. It's kind of like a RTD. You kind of have a pretty straight line, but the semester is a very big curve. So this is also a very important thing to know. The semester output is non-linear, so it's not a straight line. You're probably going to get question ask which one have negative temperature coefficient, or which one have positive temperature coefficient, which one is the most non-linear device. So if you don't pay attention to those, nobody can help you. For the semester also, they will use they will have something called a cold junction compensation. The purpose for that is for to make your measurement more accurately, to make the temperature measurement more accurately, because you use this junction to make the measurement, and you will have a cold junction compensation to make sure the measure the temperature is very accurately. What they did here is they showed you just a electrical circuit. Here's the hot junction, here's the cold junction. I believe they try to do here is using certain type of the bridge circuit, try to make sure the output will be matching whatever the temperature difference. 2020. Haiti. Heidi, what's your question? Jack 2022. Then finally here they're talking about the integrated circuit temperature transducer. So they using either a semester or they using an RTD. Oh, no. Even I came from Asia, and I'm Asian people. I cannot. I don't think I'm really good here. Oh, okay. I want you guys to pass. The integrated circuit temperature transducer is they could be inside. They have a thermistor or they have a RTD, or some of them even using thermocouple, but they made a whole package together. They can have a standard output for that. They might have a supply voltage down here. So here is a temperature measuring the IC transducer, and depends on application, depends on how they made them, and they can measure different temperature things. Those things is very accuracy, and they have a very most linear temperature and the output relationship. Okay. This picture is on your book. If you have the book, it's on page, on my book, it's page 5-12. Oh, Justin, you've never been in my class before, right? Talk to the guy in my class before. When I gave a hint, will I be lying to you? I don't lie to people. Yeah. 5-12, that's your page number, or take a picture of this one. Either get a screenshot and or whatever. This is a very, very important page. You might get, because it's a random question, there's a few questions relate to this page. Yes. I told you, when you do this exam, you better have this page with you, okay? So in this page, they give you the thermocouple, the temperature, and the voltage relationship. They give you RTD, the temperature, resistance, voltage relationship, thermistor, IC, transmitter, and you can look at this picture. Maybe we will cover everything on top. We say, okay, which picture representing a thermocouple? Which picture representing a RTD? Which picture representing a thermistor? Or which page representing an IC temperature transducer? Right? And you can also, looking at those pictures, you probably can understand which one have a negative temperature coefficient, which one the output is more linear. That makes sense? So make sure you got this page with you when you're doing the exam. Because they calibrate, because when they make this IC, they have all type of electronic device and compensation device to make to calibrate, to make sure the output is very linear. Let's can show you a video. I was talking a lot. Maybe we just stop here for a second. Let me see. What's the next page? Yeah, we're gonna stop here for a second. I'm gonna show you a video. Not video, it's a so this is a different material for resistance temperature detector. Electrically conduct metal proportion to temperature, which they are exposed. They have 3 different type material down here. The metal resistance increase, temperature decrease, the metal resistance will decrease. Some type metal used in temperature sensor device called a resistant temperature detector. So those are the picture. I have I think the other day I show you one of these without a wire. You have a connector at the end. Over the temperature range, the RTD operating within resistant temperature curve is very linear. So in certain range, that would be that. First, we connect an ohmmeter. Insert hot water, record the temperature. Then they tell us resistance is not ohms. So here, 95 degree, we have a 137. So that's the one. So that try to show you how to use this table. It's a 50 down here, it's 45 down there. Oh, 2. So measure the 102 is somewhere close to here. Is 0 degree, 5 degree. Okay, now negative, positive?
Positive.
Positive, good. Who chose the A? Eric Davis. Temperature RTD increase, the resistance typo, okay. Resistance increase, right? Just the reference. Determined temperature if ohmmeter 71.64. 71.64 is somewhere here. So we see it's -30. Good, you guys are expert now. Okay. So we are halfway. I think we are halfway or more than halfway. We are more than halfway into the module 5. And for module 5, you will have about 7 questions. So module 5, those major things, thermocouple, RTDs, semester, those are fields, lots of questions just came from there. And for the picture, I ask you guys to remember. And when we go through them, we're talking about a bunch of things. So those are most important thing you have to know. Tomorrow morning, we finish module 5 pretty quick. And then module 6 and 7, it's not a big section on there. We're only gonna give you a few questions. It's more related to an engineer when they designing a control system. That's module 6. And the module 7 is how those valves, the final control element down there. So we're not gonna have too much question on there, and we're not gonna be looking at every detail through there. So we probably, I hope we can finish everything tomorrow morning. If not, we're probably just gonna drag into the afternoon a little bit. Then the rest of tomorrow afternoon, I will be here, just try to answer your question. Yeah, 1 and 2 is the big one. 1 and 2 have 29 questions. That's about almost like a 60% of your exam. Another one is you can try to do those online quizzes. The online quizzes have a lot of similar questions as you will see them on the exam. And trust me, I don't lie to people. If I told you to do something, you do it, you will get a good mark. And if you come to my class, you're writing down everything I say is important, or you're taking notes on everything is important, you will be doing pretty good on this exam. Okay, it's close to 2 o'clock, so if you don't have a question, just go study yourself, and I will be stay here a little bit if you have questions. Yeah, see you guys. Yeah, you're welcome. You guys are a good group of students. Yeah, Hayden, you are a good student, and you have the most bonus mark. Okay. Oh, you're welcome. I think I'm only doing my job. Oh,
Hey Jack,
yes.
I had a
Yeah.
question there. Yesterday we did we're doing the module there, and then at the end we were doing table 15-2 0 to 100% output signal versus common dimensional range.
Mhm.
And there was like a table that had like the output units and percentage, and then had the output value for signal, and where's it, where can I find that?
You mean the working sheet?
Yeah, like I can't find that working sheet. Or with that specific one. Had like the percentage, and then had the milliamps and the voltage and the PSI.
I think it's in module 2. If you look at the module 2. The last two under the module 2, one is the calculation working sheet, one is signal to signal conversion. That's the one you're asking?
I think so. Yes, that's the one, I think. Yeah. Okay, thank you.
Yeah, no problem. Heidi asked me, is there any example last voltage to temperature example? Voltage to temperature example. You mean module 5 those things? Let me see. Oh, those things? Yeah, you don't need to worry about it. No, it's a different program where, like from the chart, find those temperatures. No, you don't need to worry about that. Just try to show you how they use the chart to find the temperature, but you will never use that.
Hey, Jack,
Yes.
is there any other quote unquote missing information on these other PowerPoints? Like from 1 to 4?
I don't think so. Like usually, I think some people was watching me while doing them, and they will mention. And also another thing is, if you've been in my class, you don't need to worry too much about that PowerPoint. The PowerPoint might have extra material, but what's important to you and you have to know, I already give to you.
Sounds good.
So Travel, don't make me disappointed. I'm watching you. You better get a good mark on this topic.
Oh, I'll try. I might need to redo a lot of module 1 and 2, but yeah.
No. Don't give me the same excuse like you did on year 3. I don't take those anymore. Okay?
I won't. We're good.
Sorry. I'm not trying to scare you or whatever. I know you're a good student.
Thanks, Jack.
Yeah, actually, I believe in third year you actually helped a few other guys, like Andrew. I think
Yeah,
Andrew was
got
in
it.
my last class. Yeah.
Hey Jack, I had a question.
Yeah.
I guess not so much a question about our topic, more so about doing tests online.
Mhm.
This is my first time doing the online school.
Yeah.
I did pretty well in first, second, and third year, but my first test, my first online test, I was a little surprised because I was fairly confident and only got 75%.
Mhm.
And I just wonder if you have any tips on doing the tests online, because it definitely threw me off that I wasn't able to go like back to check my work, and you you can't skip stuff if you're struggling with the question. Like, just wondering if you have any tips for working
Yeah.
around the.
So this is your first time, right? First time gonna be tough. We understand because you never have experience, never figure out a way how to do it.
Yeah.
My suggestion is because you'll never know, because usually paper version exam as a normal instructor, I just say normal instructor, I don't want to, we will not put the hardest question at the beginning, right? We want to lead the student into the exam not in a nice flow. So we always give some nice, easy question at the beginning. So build up students' confidence. Then when they keep doing things, we might throw few little bit hard question in there. But in the middle, you guys doing the exam so much, when you saw that hard question, you just can skip it, go forward, finish everything, come back, right?
Yeah.
But the online one is different because one thing is you're gonna be randomly picked, and especially one question at a time. You cannot go back. So my suggestion is every exam they have a time limit. Let's say for this topic exam, you have 50 questions, you have 2 hours. So you have 120 minutes for 50 questions. Each question going to take you about 2.5 minutes. That's roughly, right?
Right.
So roughly there will be some easy question. There will be some little bit hard question. So my suggestion is you always have a clock right in front of you, right?
Yeah.
Either on your computer or something. You can, if you think of the computer, because you focus on there, you forget to look at the clock, get a big, either your cell phone or anything to display a clock on there, right?
Yeah,
So,
I believe the test itself had like a stopwatch on it for that.
okay, so that's also a good thing, right? When you do it, if you kind of have to kind of judge in your time. So 50 questions, you can divide 100 into 5 sections. So you have 24 minutes for each 10 questions. So you kind of I know it's lots of extra stress you shouldn't be experiencing, but normally if you encounter a question, the question take you more than 5 minutes, just give up.
Yeah.
It take you twice the time, give up. Right? Just if it's a multiple choice, choose one, give
Yeah.
up. If it's a calculation, do the best, just come up with a number. Because maybe later on there will be easy questions. I heard people said, "Oh, I don't have time to finish the last few. If I have just few more minutes,
Yeah.
I can get them right." But right, so that's kind of like a time management.
Yeah.
And
My problem was I went I went too fast because the very first question on the test was hard for me for high voltage. And so I spent like 10 minutes on it looking through the code book trying to find the answer, and I couldn't find it. So I finally just guessed. And then I was freaking out because the first question took me 10 minutes. So I like blasted through the next 20 questions. And then I was like, oh crap, I have like 2 hours to do the last 20 questions. So like I think, yeah, it's just the time management.
yeah, so the time management is really important because before each exam, you will know how many questions down there, what's the time you have. So get average like in this exam, 2.5 minutes for each question. If a question take you longer than 5 minutes, it's really not worth to do it.
Right. Okay.
Right. But you will have some question you look at it, you say, oh, that's the answer. So some question going to take you less than 30 minutes. So for your high voltage exam, like you said, we usually doing paper version, we now put that hard question right at the beginning, right?
Yeah, definitely threw me off. I was still probably half asleep, and then the very first question, I was like, "What the heck is that?"
Just like a hammer on your head.
Yeah, exactly.
Wow. Yeah. So, but after that, you probably you don't also want to rush up. Like for my topic, it's pretty clear. You have 9 calculation questions. So some of the calculation questions might take you slightly longer, and other question mostly is multiple choice. Some of the multiple choice you have to think a little bit, right? But
Right.
there's a easy question in there also. So you can, if you encounter, let's say at the beginning, you suddenly encounter a hard question, take you more than 5 or 6 minutes, give up. But at the end, let's say you only take 1 hour, you already finished to 40 questions. Then you can give yourself extra time.
Give yourself 10 minutes for the rest of the questions or something.
Yeah, right?
Yeah.
So that's all you can do because for this situation, you got to understand from the school point is they don't want people to cheat each other.
Yeah.
I heard because last
some-
year I was teaching year 3, and one instructor he know one guy is cheating. He was just watching the guy, and he saw the guy was doing exam. He got like a 40, 50 something, but the guy was taking all the time. That time we still allow students to go back, right? So he did pretty bad. Then when lots of people already finished the exam and he's still there, for the last 10 minutes, he will go back to change the answer for about 10, 15, or 20 questions. He will get all those questions right in the last 10 or 15 minutes.
Every single one that he went back to, he changed to the correct answer all of a sudden.
Yeah, so we know that's not possible, right? Even on the paper version, we saw students in the class, sometimes you change it right to wrong, sometimes you change it wrong to right. But you will not have 100% chance to, oh, I got all my wrong question to right.
Yeah.
Yeah, there's plenty of times on these online tests, 'cause I've done second and third online, where I'd go back, I'd redo, like literally go through my entire test again if I did it quickly, and I would change a bunch. And I shit, you know, a lot of them I changed to wrong. A lot of them.
Yes, I saw your exam before.
Yeah,
I
yeah,
know
you
that.
know from Transformers. You yelled at me for it.
Yeah, but he's just can change all the wrong to right in just the last 10 or 15 minutes.
Yeah,
That's not
never
possible, right?
One
So
thing I saw in the Discord, somebody had an idea, and I thought it was a pretty good idea, is just release the questions in like groups of 5. So like you have 5 questions, and then you can say, okay, I want to take 25 minutes to do these 5 questions or whatever, and you can cycle back and forth between those 5 questions if one is too hard. And then you kind of solve both problems like that. You can't go back for the whole test, but at least those 5 questions, you can kind of do them in the order of easiest to hardest and go back and forth. And then that would kind of eliminate the problem, and you would still get to kind of go back and double check your work.
I think they for a while they tried to divide the whole exam into a 3 section or 4 section. They tried once. Then someone said it didn't work out. Like, hey, you guys want to invite me into you guys' Discord group? You probably don't, right? That's okay. That's fine.
No comment.
We actually have a 1 or 2 term before. I think 2 term before. We got reported because some there's the people have a very righteous people. They send the chief instructor an email with attached picture of people in those online chatting. Like I forgot it's a Discord or WhatsApp. Some people doing the exam time, they take the screenshot, they post the question on the, I believe it's a WhatsApp or Discord, I forgot. They ask, hey, what's the right answer for this question? Then there is people giving the answer for that.
Yeah, some people are pretty stupid, and they, with their actual name, will go and try and cheat on the Discord.
Well, the thing with those guys doing that, it just screws them in the end, though.
Yeah.
That's why I just don't ever see the point in that. If it comes to the IP, you're done.
IP.
Yeah, but you gotta understand there is a company like I'm not because I would say Asian company, right? And they don't require people to pass the IP. They just if you pass 4th year, you become a journeyman. That's good enough because they can pay those guys lower.
Yeah, some people are completely content with being like 8th term or permanently a 4th year apprentice.
So there's the people only want to cheat through the school year. They don't care about the IP.
Yeah, that makes sense.
Right. And so that's why it's a continuous. For me, I usually, okay, if you ask me, I think every student should pass. That's my idea. But they have the school system here. Someone try to maintain. I think integrity is an important part, but
of course,
I think because I don't know how people think. As a still apprentice or journey person, how much calculation of those things you actually do on the job compared to you come to school, we ask you to do so much thing. Right.
Well,
but
how much stuff, if you're really in a bind, can you just Google it or look it up in an online code book on your phone?
Yeah, but in here is certain people or certain instructor we have. You guys are lucky this term. You don't have those type of instructor to just think, oh, you have to know everything.
Yeah.
So I have no. I usually don't say anything. I just do my job, and the other instructor they complain, they do whatever they want to set the system so student cannot cheat.
Mhm.
Whatever the policy they taking, I just go with it. For me, I just do my thing. Is I will try to help a student to pass, but I cannot just say like a spot I will say, okay, here's a test question. Go do it. Then tomorrow you will have the same exam. I cannot do that, right? It's a BCIT. So go through my lesson. I will tell you what's important. You have to know.
Yeah, that makes sense. Are
So
you doing this next week, Jack? I haven't looked at the schedule.
next week, I think you guys with Jeff for
Back-
modern building system. Then you guys gonna with me for the renewable energy and emergency power.
Okay. Cool. Well, thanks for answering my question. That helps a lot. I'll see you tomorrow at 8 a.m.
Yeah. Okay. See you.
Thanks, Jack. Bye.
Have a good day. Bye.
Oh, welcome. No, there's no retest. We only have you only have one chance to do the exam. Some of the topic I try to help you guys to get a higher mark, so you can compensate for the low mark you're getting lower. But it's the thing is you don't come to my class, then you gotta go study everything. You come to my class, you should be getting pretty decent mark in my class. Okay, guys, all good. So I'm gonna be ending this meeting. I will see you guys tomorrow morning.